Hello everyone and welcome to ML Done. So today we're going to start our mathematics of machine learning video with this very interesting function called the Softmax function. Now those of you who are familiar with neural networks know that we tend to use the Softmax function as some sort of a activation function in the final layer of a neural network. And that is typically used for the task of classification, because with the softmax function we tend to have some sort of a probabilistic interpretation as to what our neural network thinks about a particular input vector. When I say thinks, I mean which class does our neural network think that this particular input belongs to, right? Now, let's consider the case where we have three classes in our problem. For example, class cat, class dog, class car. Yeah? And given an input image of either of those classes, we'd like to train our neural network in such a way that it would generate the right value on the output layer, meaning that if the image belongs to class cat and we have three classes, we'd like our neural network to generate a high value on the neuron, on the output neuron that belongs to class cat, and a very low value on the output neurons that belong to the classes dogs and cars. Yeah? And if the image belonged to class dog, likewise, again, so the output neuron that belongs to class dog should have so the neural network should learn to generate a high value out of that particular neuron that belongs to class dog, and a very low value out of the neurons that belong to classes cats and cars. Yep. Anyways, that was just a very short interpretation as to, well, not interpretation, but very short explanation as to where we use softmax function and how we use it. A very broad picture. Well, this is not a neural networks video, so I'm just going to focus on the mathematics behind this, okay? Now, imagine that we have a vector. Yes. Let's call the vector z, right? And let's say that z equals z1, z2, and z3. So it has three elements. Yes? So these elements, z1, z2, and z3, are actually the inputs to our softmax function. So in other words, the main input to a softmax function is a vector called the actual z, where we have it over here, right? So it's the big Z, and it has elements z1, z2, and z3, right? So interesting enough, the softmax function would also output a vector of the same size as z, and it would have, again, three elements, right? Now, I want to show you how a particular element of this output vector would be computed by the softmax function, right? So far we haven't really talked about the partial derivative of the softmax function with respect to these elements. So far I'm just warming up to the idea of the softmax function. I want you to feel more comfortable with it, okay? Let's understand what it does. Now, we know that the softmax function, let's use color red. Let's show that with S as softmax, yeah? We know that S of, say, Z1, the first element. The way we compute this, actually you might already know this, but it is equal to e to the power Z1. Yeah, I think we need to go a little bit higher, yeah. So that would be e to the power z1 divided by the summation of everything. E to the power z1 plus e to the power z2 plus e to the power z3. Yes? So as you can see, in order for Softmax to be able to compute the output related to Z1, it needs Z2 and Z3 as well. By the same logic, if I were to compute softmax of Z2, yes, I would have had to use all the other Z's as well, meaning that the denominator only uses Z2, so it just exponentiates Z2. However, the denominator is again the same as here. It's again the summation of the exponentiation of all the Z's, Z3, yes? The same story with Z3, yeah? So we will have S of Z1, S of Z2, S of Z3, and those will be the three elements of the output vector of softmax, yeah? So in general, if I wanted to write a more general formula to describe every element of the output vector of the softmax function, the way I would write that would be like this. So S of Z of I, meaning the ith element of my Z vector, when I feed that into my softmax function, this is how softmax computes the output corresponding to this Z of I. So it exponentiates Z of I, but what it does, it computes the sum of all the other exponentiations of Z for all the Z's that you have in your vector, meaning that you would have a sum, right, of e to the power Z of j, where j goes from 1 to, say, n. N would be the total number of Z's that you have, basically the length of your input vector, big Z, right? So here n is 3. So e to the power Z1 plus e to the power Z2 plus e to the power Z3, that would be the denominator over here, yeah? And the denominator would be just the Z of I that we are interested in. But it could be Z of 1, it could be Z1, it could be Z2, it could be Z3, yeah? So far so good. This is the softmax function. And even more interestingly, because for every one of these elements, Z1, Z2, and Z3, we have a common denominator for all the three different softmax values. The summation of all of these outputs will be 1, meaning that if I were to say, for example, in here, softmax of Z of 1 plus softmax of Z of 2 plus softmax of Z of 3, it will sum to 1. You see, now it makes more sense why I said that you can interpret softmax as a probabilistic approach, as a method that could give you probabilistic interpretation, because the sum of the elements of the output of softmax would all be 1, right? So that's the same rule that we have in probabilities. So the probability of all the outcomes always has to sum to 1, right? So that is one of the reasons why you can use softmax in that sense. So if I were to write this rule, the summation rule, as a general mathematical formula, all I have to write is summation of softmax of I for I from 1 to n would have to be 1. Actually, it is 1. It's not something that we're going to have to enforce, because as long as we follow this formula, for every Z of I, the resulting softmaxes, the resulting values, they will all sum to 1, because of the common denominator that we have here. The interesting part about the partial derivative of softmax with respect to its inputs, Z1, Z2, Z3, You notice that for computing the softmax of every element of Z, you're actually using all the other elements of Z as well, right? So for softmax of Z1, even though we have e to the power Z1 here, but we have summation of Z1 plus Z2 plus Z3 in the denominator, right? You would have to do this for softmax of Z1, softmax of Z2, and softmax of Z3. So in other words, if you were to compute the partial derivative of the entire softmax vector with respect to, say, just Z of 1, you're going to have to compute the partial derivative of all the elements of the output of softmax with respect to Z of 1. The same story goes with Z of 2, the same story goes with Z3, right? So in other words, I'm just going to keep it over here. In other words, if I consider S of Z as a vector of softmax of Z1, softmax of Z2, and softmax of Z3, in other words, if I wanted to compute the partial derivative of my softmax with respect to, say, Z1, yeah, that would be, for that, I'm going to have to take the partial derivative of S of Z1 with respect to Z1 and partial derivative of S of Z2 with respect to Z1 and partial derivative of S of Z3 with respect to Z1. Because, as we said, S of Z1, S of Z2, and S of Z3, they're all a function of Z1. They're also, all of them are also a function of Z2. And they're, again, all of them are also a function of Z3, right? So for taking the partial derivative of your entire softmax function with respect to a particular Z, you're going to need to take the partial derivative of all the elements, meaning S of Z1, S of Z2, S of Z3, all the way with respect to that particular Z that you're interested in. Okay? Now, I want to do this mathematically, but in order to make it a little bit simple, I'm going to use our toy example where we have only 3 elements in our Z vector, which will be the input to our softmax, and just show you the partial derivative of S1, S2, and S3 with respect to only Z1. And then you'll see the outcome. A pattern will actually emerge, okay? Now, let me just erase all of these. So we have our Z vector over there, and we have our definition of softmax over there. Yeah. Now, let's consider, because let me just tell you again what we're doing. We're going to compute the partial derivative of S of Z1 with respect to Z1, and then partial derivative of S of Z2 with respect to Z1, and then partial derivative of S of, that's right, Z3 with respect to Z1. So these are the things that we're planning on computing, right? Then you'll see a pattern emerging. Now, let's start with S of Z1. Let's first mathematically write it. So, actually, I don't even need this. Well, we already talked about this. We have 3 elements because I need a little bit more room. Yeah? Now, S of Z1 equals, based on our definition, e to the power Z1 divided by e to the power z1 plus e to the power z2 plus e to the power z3. Yes? Now I want to take the partial derivative of this guy with respect to only z1, meaning partial derivative of s of z1 with respect to z1. Now, you know from basic mathematics that there's a rule to taking the partial derivative of a fraction, yeah? And that rule is that if we have, say, f of x divided by g of x, and we want to take the partial derivative of this whole thing with respect to x, then we'd have to say that this equals partial derivative of f, or it doesn't even have to be partial derivative, you can also say derivative. Let's go with derivative for the sake of brevity, and that would make the whole explanation a little bit easier and faster. Right, so the partial derivative of this entire thing with respect to x, or the derivative of the entire thing with respect to x, would be the derivative of f with respect to x multiplied by g of x minus the derivative of g of x multiplied by f of x. Yeah. The entire thing divided by g of x squared. Yeah. Number two, there's another rule that you need to know to get more comfortable with this entire derivation. The derivative of an exponential function, if I take the derivative of this guy with respect to x, we know from basic mathematics that it's actually equal to the same exact exponential function. So this equals to e to the power x. Yeah? And you know that if I had, instead of x, I had some other variable here, like y. Yeah? So derivative of a function that is not a function of y with respect to y. It means that what is the rate of change of this function with respect to something that doesn't even exist in that function? So the rate of change would be 0, meaning that e of e to the power x is independent of y, right? And that's it. Last but not least, actually, there's another rule that I'd like to point out here. And that rule is called the derivative of summation. If you have, say, 3 functions, or let's make it simpler, 2 functions, h of x, you're summing it with another function, let's call it g of x. And you want to take the derivative of the entire thing with respect to x. So you're taking the derivative of a summation with respect to a variable. Yeah? So the rule says the derivative of a sum is the sum of derivatives, meaning that this entire thing equals the derivative of h of x with respect to x plus the derivative of g of x with respect to x. So the derivative of the sum equals the sum of the derivatives. Sum of the derivatives. But these are the only things that you need to know to really understand the partial derivative process of the softmax function with respect to its inputs. Let's take the partial derivative of this entire thing with respect to s of 1. So the rule of fraction says the derivative of the numerator multiplied by the entire denominator minus the derivative of the entire denominator multiplied by the numerator, and then the whole thing divided by the denominator squared. Perfect. Now, I want to make this a little bit simpler. So the partial derivative of s of z1 with respect to z1. What is the partial derivative of the nominator? It is e to the power z1, isn't it? With respect to z1 would be itself. That's the exponential rule that we just talked about, right? So that would be e to the power z1. I'm going to multiply that by the entire denominator, yeah? The entire denominator would be e to the power z1 plus e to the power z2 plus e to the power z3 minus the partial derivative of the entire denominator multiplied by the nominator, yeah? So we have e to the power z1 that depends on z1, but we know that e to the power z2 and e to the power z3 don't depend on z1, right? So if I were to say the partial derivative of the entire denominator with respect to z1, then the second and the third element will zero out because they don't depend on z1, but the first element does depend on z1. So because of the law of summation, as we said, the derivative of a sum equals the sum of derivatives, right? So derivative of the entire sum would be the sum of derivatives. So that would be the derivative of e to the power z1 with respect to z1, which is itself, plus derivative of e to the power z2 multiplied with respect to z1, which is 0. Same story with e to the power z3, 0. The entire thing multiplied by the denominator because of our law of fraction, right? So the derivative of the denominator multiplied by the nominator. Now, the denominator plus e to the power z2 plus e to the power z3 squared. Yeah? Now, you see over here, I can just make it look a little bit nicer, right? Because 0 doesn't matter. I can just get rid of the zeros. Yes? And then e to the power z1 multiplied by e to the power z1 is actually e to the power 2z1. Yeah? That's the law of multiplication of numbers with power. Yeah? So e to the power z1 multiplied by e to the power z1 would be e to the power 2z1. Yeah? Number 2, a more simplifying step is to get rid of this notation over here. Let's make it a little bit simpler. So let's show this summation with sigma, big sigma, because, well, traditionally it is a symbol for summation, right? So instead of this gigantic thing over here, I'm just going to write sigma. And instead of this thing squared, I'm going to write sigma squared. Or sigma multiplied by sigma. Yeah, both of them are the same. So instead of this thing over here, I'm just going to write sigma multiplied by sigma. And instead of this entire thing over here, I'm just going to write sigma. Yeah? Perfect. So far, so good. Now, we're going to play a little bit of trick here. Yeah. If I factor e to the power z1 out of the denominator, what's going to happen? Equals, can you see? Yes. E to the power z1, factor it out. Sigma will survive, minus e to the power z1 again, divided by sigma multiplied by sigma. Yeah. Now, here's the interesting part. Let me just get rid of the bit on the top. Here is the interesting part. We can actually separate these two from each other. Yeah? And how do we do that? We can consider this portion multiplied by this portion, right? So what would the first portion look like? E to the power z1 divided by sigma, right? So if I were to write it here, let me just get rid of it and just start writing on the top. The first portion, remember, this is still the partial derivative of s of z1 with respect to z1. So the first portion, e to the power z1 divided by sigma, that would be 1 with respect to sigma, yeah? The entire thing multiplied by the second portion, yes? The second portion is sigma minus e to the power z1 divided by sigma. So these two parts are getting multiplied together. Yeah. Now, let's dig deeper. You see, it's a little bit tricky. It's not the most convenient derivation. Yeah. So, does this look familiar? It's actually softmax of z of 1, isn't it? This is actually s of z1. We've seen that. And this second term over here, you can actually divide by the denominator, and this would be 1 minus e to the power z1 divided by sigma, right? So in other words, this is 1 minus e to the power z1 divided by sigma again. Look, this again is familiar. This is again s of z1. So we have s of z1 multiplied by 1 minus s of z1. Yeah? So in other words, the partial derivative of s of z1 with respect to z1 equals s of z1 multiplied by 1 minus s of z1. So, it was tricky, a little bit tricky, but once you really understand the basics, the basic mathematical stuff behind it, it becomes quite simple actually. So you need to just go over this a little bit more, maybe a few more times so you really get comfortable with it, yeah? Remember, we said that we need to take the partial derivative of s of z2 with respect to s1 and s of z3 with respect to z1 again, right? So it's not just s of z1 that we have to be concerned with, because s of z2 and s of z3 are too a function of z1. Now, so this was the story with s of z1. Now, we're gonna do the same with s of z2. What was s of z2 again? It was s of z2, it was equal to e to the power z2 divided by the denominator, yeah? So which was e to the power z1 plus e to the power z2 plus e to the power z3, yeah? So I'm gonna go a little bit faster here because it's almost exactly the same as the previous step. Only one part changes, yeah? Now, we're gonna say the partial derivative of the numerator multiplied by the entire denominator. The numerator is e to the power z2. Derivative of that with respect to z1 is 0 because they're independent of each other. There's no z1 anywhere in this numerator. So the partial derivative of s of z2 with respect to z1 is the derivative of the denominator is with respect to z1 is 0 multiplied by the entire denominator, again is 0, so we have 0. That's the first difference between this and the previous case, minus the partial derivative of the denominator with respect to z1. This term cancels out, that term cancels out, only the first term survives, yeah? So we have e to the power z1 multiplied by the nominator, right? So that would be e to the power z1 multiplied by e to the power z2, right? And then the denominator squared. So we said that we're going to show the denominator with just a big sigma, right? Let's make our life easier. That would be sigma squared or sigma multiplied by sigma, right? And we know that this 0 can be just deleted because that really doesn't matter. Now, again, let's see the two different portions. The first portion multiplied by the second portion. The first portion is, let's just not forget about this minus. Minus, let's just leave it here. E to the power z1 divided by the sigma. That's familiar. That's actually s of z1. E to the power z2 divided by sigma. That's also familiar. That's s of z2. So let's write it as it is. S to the power s of z2, right? So we see that once we are taking the derivative of z2 with respect to z1, we get minus s of z1 multiplied by s of z2. So this is different from the result that we got previously. So what's the story there? Now, what would happen if I take the partial derivative of s of z3 with respect to z1? Can you guess what happens? It's exactly the same as this step, except in that case, the result would be minus s of z1 multiplied by s of z3. That's the only difference. Now, there's a general rule. You might have guessed it by now, actually. If you're taking the partial derivative of s of, say, zi with respect to zi, or let's call it with respect to zj, if I and j are the same, meaning that you're taking the partial derivative of s of z1 with respect to z1, or maybe s of z2 with respect to z2, or maybe s of z3 with respect to z3, we always fall under the first rule, the first thing that we derived, right? But if those indices are different, I and j are different, meaning that the partial derivative of s of, I don't know, z3 with respect to z2, or s of z1 with respect to z3, then this is the rule. We're going to have minus the multiplication of s of z1 and s of z2, s of z3 and s of z2. Yeah? So what's the general pattern, the general rule? Now, this is the thing that you see on many blog posts, this final step that shows you the entire pattern, the entire mathematical rule for taking the derivative of softmax function with respect to its input. Now, if my softmax, I have my softmax, right? If I say what's the partial derivative of s of, let's call it zi, with respect to zj, two things could happen. If I and j are equal, which was the first case that we derived, meaning that if I equals j, in other words, if I'm taking the partial derivative of z1 with respect to z1, sorry, s of z1 with respect to z1, or s of z2 with respect to z2, or s of z3 with respect to z3. In those cases, that's when I and j are equal. In that case, the rule says, you will say that would be s of zi multiplied by 1 minus s of zi. That was the first thing that we derived. But if they were different, I and j were different, partial derivative of S of Z3 with respect to Z1, right? 3 and 1 are different. In that case, the result is minus S of Zi multiplied by S of Zj. So this is the softmax function, the derivative of the softmax function with respect to its inputs, right? You do the same and you compute the partial derivative of your softmax with respect to any of the inputs of your interest. Now, it was a very maybe tense session, a little bit complicated at times, but I would strongly recommend you to go over it a few more times yourselves. Try to really understand the basic of the mathematics in each individual step to get more comfortable with it. You will never really get it unless you do it yourself on a piece of paper. That's the only advice that I could give you. So I hope that this has been informative for you. If you have any questions or comments, please just leave them in the comments below the video. If you enjoyed the video, which I hope that you have, you could just subscribe to my channel, MLDon, and also click on that bell-shaped icon so that you'd be notified when I upload a new video. And you can also follow us on Twitter, LinkedIn, Facebook. All the links are in the description to this video. Plus, I have posted a very nice blog post on my website, mldon.com, where you can also see all of these in detail, all of these derivations in detail, so that you could follow the math from a written post as well, because some people are more comfortable with reading the stuff rather than just watching a video. So I hope that this has been informative for you, and thanks a lot for watching.